This video is going to be about limits of functions, the first lesson in our calculus unit. So it's helpful to start thinking about limits by looking at the graph of a function. So here's a function f of x equals 1/2 to the x power. And we're told to use a GDC, that's a graphing calculator, to examine its behavior for large positive values of x. So basically, we're going to look at the graph and then look on the right side of the x-axis as x gets bigger and bigger and see what's happening to the values of the function. So here's the graph. If you take out a graphing calculator and input this function, it's going to look like this. We're only seeing -10 to 10 on the x-axis, but you can already see, just as x is 10, what's happening to this function. So the function is the blue curve. It's sweeping down from up at infinity, and it's approaching 0. In fact, it looks like it actually is lying on 0 when you look at where x is 10, but it's actually just a teeny bit above 0. And as that x value gets bigger and bigger, to 10, to 100, to 1,000, that blue line is getting closer and closer to the x-axis, and it'll never actually reach it. So we might say that the limit of this function as x goes to infinity would be 0. So it's approaching 0, knowing that it's never actually going to reach that. You can prove this to yourself by looking at the table for this function. So if you're looking at the graph on an Inspire calculator and you hit Control-T, it'll split screen and give you the table next to the graph. So if you do that and you look at, these are the x values in this little tiny left-hand column, when x is 0, when x is 1, when x is 2, and look at the values of y, which is the function, right? When x is 0, the function's at 1, and then it's at 1/2, and then 1/4, and then 1/8, and then it keeps getting smaller and smaller and smaller, all the way up to over here where you see x is 18, and look how tiny the value of that function is, 0.000004, and getting ever smaller, but never reaching 0, so getting closer and closer to 0. That's sort of the idea of a limit for a function. So let's see what this notation looks like. You could conclude that because the function is getting closer and closer to 0, the limit as n goes to infinity, in fact we were using x, so this could look like the limit as x goes to infinity, of the function 1/2 to the n power, right, that's what the function is equal to 0. So that's how you would read it. In quotations, it says below how you read that. The limit as n approaches infinity of 1/2 to the n is 0. So that just means as n approaches infinity, as n gets bigger and bigger and bigger, so the n up here, as it gets bigger and bigger and bigger, like 1/2 to the 10th, 1/2 to the 100th, 1/2 to the 1,000th, the limit of the function is 0, even though it'll never actually reach it. So that's your first view of a limit notation, okay? Sometimes you can get a limit by just substituting the value. So in this example, and in fact this should be x based on the way that the function is written. In this example, this is asking for the limit of the function as x goes to 6. So it's not even talking about the extreme right side of the graph as x goes to infinity, or the extreme left side of the graph. It's just talking about at a specific point on the function. So as x goes to 6, what is the value of the function x over 2 minus 1? So I did get this one, a graph over here. I wouldn't actually need a graph. I just want to show you why. At the point where x is 6, that's like 1, 2, 3, 4, 5, 6 right here, the function exists at a very concrete point, right? It's not approaching a value that it'll never reach or something like that. It's a fixed point, and the function has a value there, so you could get it in this limit question just by plugging in 6 where you see x. So if it's a nice simplified function like this, and you're evaluating a limit at a concrete point, try plugging in the number and see if it gives you an output. So 6 divided by 2 is 3, and 3 minus 1 is 2. So the limit of this function as x approaches 6 is just 2. That's always how you're going to want to start doing these, right? By substituting in a value. And you can even imagine substituting in infinity. However, before you substitute in infinity or any number to check your limit, it's going to be helpful to simplify your function. So a fully simplified expression where the little function appears. So in this case, it looks pretty good, but I could simplify this even a little further and make the limit easier for myself to do. So the limit as x goes to infinity, right? We're not going to evaluate that yet. We're going to simplify this to 5x over x and minus 3 over x. So when you're looking at an algebraic fraction, see if you can simplify it first. Because it's just over a monomial x, I can separate it this way. And this one simplifies nicely to just 5. So now I'm looking for the limit as x approaches infinity of 5 minus 3 over x. This is as simplified as it gets, and so now I can imagine substituting in infinity, which is basically just an extremely large positive number, to see what the value of this function would be, just like when I plugged in 6 to the previous one. If I plug in infinity here, the one thing you have to understand is that when infinity is on the bottom of a fraction, like 3 over a huge, huge, huge number, that's actually an extremely small value, right? 3 over an ever bigger and bigger and bigger denominator is a smaller and smaller and smaller fraction. You can prove it to yourself just by imagining 3/4, that's like shading in, 3/4 of a circle, versus 3/10. Already that's a much smaller quantity, versus 3/100, right? That's a much smaller quantity. And so you can imagine as that denominator gets close to infinity, how tiny this fraction actually is. It's so tiny, it's basically 0. And so what we're doing for this limit, if you imagine 5 minus 3 over infinity, that's basically like saying 5 minus nothing as that infinity gets ever greater. And therefore, the limit of this function as x goes to infinity would be 5, right? The limit here is a concrete number, 5. All right, in some cases, the limit of a function is itself a function, and that's not quite accurate to say. This is not really a function, it's an expression, this 3x squared minus 4px plus p squared, because p is unknown. And we're asked here to find the limit of this as p approaches 0. So that if there's 2 variables going on, or even more than 2 variables going on, you're going to use the substitution thing that we just did, but just for the variable at hand. So here it says p should go to 0. The limit as p goes to 0, and then we're going to see what remains when we make p be 0. So first I'm looking at the expression and seeing if it's fully simplified. This one is. I don't see anything I can combine. It wouldn't help me to factor this. In fact, it's better to look at it like this. I'll expand it out. So I'm ready to do the limit by substituting in 0 for p. And what I get when I do that, right, would be 3x squared. There's no p in that term. 4 times 0 times x. Notice I'm just leaving x as x plus 0 squared. Well, 0 times anything in this term is going to make this term go to 0. 0 squared is 0. So really, the limit of this function as p goes to 0 is just the first term. And that's going to be much, much more applicable when we start diving into some of the calculus. But just I wanted you to have that, that visual that if there's more than one variable going on, just make the variable in question become the 0 or infinity or 6 or whatever you're asked to plug in, and leave all the other variables alone, and then simplify. This is as complicated as it could get. It looks like, all right, I have this complicated expression. It says limit as h goes to 0, so I should just take all these h's, make them 0, see what I get. Sort of like the example we just had where we made all the p's be 0. The problem being this one's simplifiable at the beginning. There's something we could do to this to make it more simplified. And indeed, in order to do this limit, we have to. Because if I start doing the limit right now when h becomes 0, this is undefined, and it's not okay to do that. So we're not going to be able to do this limit until we've simplified the expression. Simplifying this expression is not as bad as it looks, but the numerator is going to get worse before it gets better. So the only way to deal with this numerator, because it has all this subtraction in it and addition, is to get it expanded. Then we're going to look for like terms to cancel out. So limit as h goes to 0, that stays there. Expand the top. I see x plus h to the second power, which means x plus h times another quantity x plus h. Therefore, it's like FOIL. All right, and that's going to give us x squared plus hx plus xh, which is 2 of the same thing, so 2hx from the middle 2 terms, and then plus h squared. Then I see this minus 6, and then I have to distribute this minus sign, so minus x squared and plus 6. And so there it is, a little bit worse before it gets better. But now you can see what's going to happen. This x squared and this minus x squared cancel out. This minus 6 and this positive 6 cancel out. And so my numerator, and I haven't done the limit yet. I have not made h become 0, so I'm going to keep writing that, is 2hx plus h squared over h. And I can try to simplify this because they're both over h, right? I can imagine either factoring out an h from the numerator or doing the trick like I did on the first slide where we're separating it into 2 fractions, both over h. I'll do the factoring method here because I think it's going to be more helpful as we dive into calculus to think about this as factoring out the h, which would leave us with 2x plus h on top, and then this h and this h cancel out. Not this one, okay? This one you cannot cancel out with the h on the bottom because it's part of a binomial expression, right? It's attached to something by addition. So now I'm left with limit, go over here, limit as h goes to 0 of 2x plus h. Nothing else to simplify, so I can now do the substitution of h becoming 0. I see that the h term just goes away. I drop the limit. I'm left with 2x, and that is the limit of that very, very complicated looking fraction at the top as h becomes 0. This particular slide is something that you're going to do a lot in this chapter. This is just your first introduction to it. Going forward, we're going to be writing our own version of that fraction up at the top, and once you've written it based on a formula that you're going to learn, then you will have to know how to simplify it and then do the limit at the very end. So we're sort of practicing the last step of a problem that we're going to do a lot later in the chapter. All right, so for an undefined case, as in this one, I want to make x 0. I see that x is in the denominator, and that's going to be undefined. And I can't simplify this fraction in any way. If you look at the numerator, it's just sine x. I cannot cancel out these x's. That's not something you can ever do because the x in the numerator is part of the sine function, right? This x is inside of this sine function. So I can't do anything like that. So I can't simplify it, and it would be undefined if I plugged in 0 right now. So you don't just get to quit and say, I don't know, or no solution. So for an undefined case like this, where you cannot simplify, you have to maybe use your calculator to look at the graph. So to tie it back to how we started this presentation, we were looking at graphs to figure out limits. There are algebraic techniques like just substituting in, but if you get back to a case like this, substitution doesn't work, you're going to have to rely on the graphing method. So let's see if I have a graph of this function on the next slide. We're looking for the limit as x goes to 0. Here it is. Okay, so here's the function sine x over x. It's graphed in radians. I'm looking for the limit as x goes to 0, right? And I didn't type in any limits or anything. I just typed in the function sine x over x. But I remember that I'm looking for the limit as x goes to 0. So if I'm looking for the limit as x goes to 0, imagine find the point on the graph where x is 0. Okay, it's a pretty concrete point right there. The function exists right there. Whether you're coming at it from the left or from the right, as x approaches 0, right, whether it's creeping up to 0 or creeping down to 0 from either direction, the function's approaching that very concrete point. Therefore, the limit of this function as x goes to 0 is 1. There would not have been any way for us to know that by substituting 0 into the function, remember, because that produced undefined. So in a case like this, you're going to want to look at the graph, and it would have to be on a graphing calculator part of the exam. So find the limit of this if it exists. So we're looking at this function. We're imagining simplifying it. There's no way to simplify 1 over x squared. I could try making x be 0, and then I realize that's going to give me undefined. So here's a time where I'm going to want to look at the graph, right? So put yourself through those steps. Can I simplify the fraction first? Can I plug in whatever it's asking me to do the limit? And if no to both of those things, go to the graph. So I've gotten a graph of this, and this is an interesting case. The graph of this function looks like this. And no matter how high you scroll up that middle, you're never going to see those two red branches of this function ever meet. They're both getting closer and closer to the y-axis, and they're never going to touch it. So at the point where x is 0, which would be like right here, right at the point where x is 0, this function never exists. And as you approach it from either side, right, whether you're coming from negative side or from the positive side, as x is getting closer and closer to 0, the function doesn't approach a limit. The values of the function are going up and up and up and up to infinity on both sides of this y-axis. So it's not like it's at a concrete point like the previous example, which was sine x over x. It's the function going up forever as x approaches 0 from both sides. So this would be a time where you can correctly conclude that the limit does not exist. There isn't a limit to this function as x approaches 0 at this point. The limit does not exist, which in a calculus course or textbook you might see abbreviated to DNE, does not exist. That doesn't mean that this function doesn't have any limits. It's just as x is approaching 0, this function doesn't have any limits. It's just rising to infinity. But let's look, for example, as when x approaches infinity. If I said find the limit as x approaches infinity of 1 over x squared, you can see what's happening. as x approaches infinity, the function's getting closer and closer and closer to 0, right? It actually is reaching a limit. And so for this one, you could conclude that the limit would be 0. Or you could imagine, as we did before, plugging in infinity, where you see x, and remembering that 1 over an infinitely large number is basically 0. That's how tiny of a quantity it is. And then we need to review asymptotes for rational functions for a purpose that you'll see on the next and last slide. So a quick review of asymptotes for rational functions. These are functions that have x in the denominator that could look one of two ways, basically, for the case of IBSL. If you look at the top function, there's just an x in the denominator. A and h and k are all going to be numbers. So for example, it could say the function r of x equals 1 over x minus 2 plus 4, right? That would be a rational function. And the asymptotes for this function, the vertical asymptote is at x equals 2. And I'm not that concerned about the vertical asymptote. Good to know, because it's a review concept. The vertical asymptote will be located at x equals 2 because that's the place that the function can't exist. It would make the denominator 0. The horizontal asymptote for a function of this form is going to be located at y equals 0. But if there's a vertical shift over here in the function, like this plus 4, that would shift the whole thing up by that many units, or down if it was minus. So you have to know that it's going to be y equals whatever that number is. Because normally, just for the plain fraction part, if you see a fraction with x in the denominator like this, the asymptote's at y equals 0, because there's no way that function could ever spit out 0. And then it'll shift up with whatever that constant is, that k value at the end. You're more likely to see a function like this, where there's a function on top and a function on bottom, and both have x in it. In this case, they're both linear, because that's what IBSL usually tests on. Right, so if you see something like this, it's a linear function on top, a linear function on bottom. The vertical asymptote is going to be following the same procedure. You're looking for what makes the denominator undefined, right? So x equals -1. But the horizontal asymptote this time isn't just going to be located at 0 with a shift. This time, the horizontal asymptote is going to be located at whatever the coefficient of x divided by the coefficient of x is. So here, that's 2 divided by 1. So the horizontal asymptote will be located at y equals, see if we can get that out of the way, horizontal asymptote would be located at y equals 2. This matters because if you're on a non-calculator part of an exam and you're talking about limits for these functions, it's really helpful to know, because a rational function is going to look something like this. Let's see. Right, it's going to have a branch and a branch, and the asymptotes are going to be guidelines for finding limits all the time. So the horizontal asymptote in particular here is at 2. As x approaches infinity, right, let me fix this branch and make it go a little further. Right? As x approaches infinity, that horizontal asymptote is telling you the limit of the function. And same thing as x approaches negative infinity. That's what a horizontal asymptote for a function actually is. It's the behavior of the function as x goes to infinity or negative infinity. So if you're not allowed to use a calculator and you're asked to figure out limits of these functions as x goes to infinity or negative infinity, it's really helpful if you can identify what the horizontal asymptote is. Of course, if you do have a calculator, you could just graph it. Right, so here's that final case. What if the limit exists, but you can't simplify this fraction? Maybe you don't have a calculator. So here's a case where if you can identify what the horizontal asymptote is, you'll know what the limit of this function is as it goes to infinity. So if I'm not able to use a graph to just see, I'm going to want to know my asymptote rules. So this is one of the cases where I have a function on top and a function on bottom. This goes a little bit beyond what SL would normally ask us to memorize, but I think that you can know this. You've studied it in Algebra 2 before. This time, the numerator is linear, but the denominator has a squared in it. So it can't just be the rule of coefficient divided by coefficient. This is where you need to know when the degree is, when the degree is, not in, when the degree is higher in the denominator, as in this case here, the horizontal asymptote is located at y equals 0. If the degree is the same, that's like the example we saw on the previous slide, it's going to be coefficient over coefficient. And if the degree on the top is higher, then there isn't going to be a horizontal asymptote. So in this case, we have degree is higher in the denominator, so the horizontal asymptote is located at y equals 0. Therefore, I know that the limit of this function as x approaches infinity is just going to be 0, just from knowing that rule. You could also graph this function on a calculator, right, if you had the calculator, and see that, indeed, as x goes to infinity, the function is approaching 0. And that should get you through the homework.